Youth.
I don't.
All right. Good afternoon, everyone. I welcome you once again to our classes today, and thank you for joining. I hope you all can hear me. Um, Let me just ask Abisola Rachel. Can you hear me?
Yes, sir.
All right. So that is very perfect. I welcome you once again today for our classes, and we will try to do justice to the topic, and then we'll try to do justice to the topics and um, continue from where we stopped. Okay, so from where we stopped, if you look at where we stopped the other time, we tried to look at the concept of autocorrelation. Okay, we started by looking at the nature of autocorrelation and then the causes. And so part of the causes of the autocorrelation is um, the inertia, which is sluggishness, specification error or incorrect functional form, specification. Sorry, someone, Adenike, please, can you mute your mic, please? Adenike, please, can you mute your mic? Okay, sorry. So I believe you can hear me now. Can I get a response from your chat? Can you hear me now? Okay, all right, thank you. Okay, so we looked at the causes of autocorrelation. We started by looking at inertia sluggishness. Then we looked at specification error, which is when we have incorrect functional form. We also looked at another case of specification error. That is where we have excluded or omitted variable case. And then we also looked at the lags and cobweb phenomenon. and then data transformation. And then we also tried further to examine the consequences of autocorrelation. All right. And then the first thing we said is that the OLS will still be linear. That's the first thing we said. And then we went further to say that when you have autocorrelation, your OLS will also still be unbiased. All right. So your OLS will be linear, your OLS will be unbiased, but your minimum variance property will be violated simply because when there is autocorrelation, the variance of the error term becomes larger. And when the variance of the error term becomes larger, the standard error, all right, of the coefficients will also become larger. And so when the standard error is larger, your t statistics for that particular coefficient becomes smaller. And when your t statistics for that coefficient becomes smaller, what happens is that you are likely going to reject your null hypothesis when you are supposed to do what? You are likely going to fail to reject your null hypothesis when you are supposed to actually do what? Reject it, okay? So the minimum variance property will be violated because when that variance of the coefficients becomes large, that means that in the class of other linear unbiased estimator, the OLS will no longer have the least variance. And once the OLS does not have the least variance, what happens next is that your OLS will no longer be blue. So it wouldn't be best. I got lost there. Probably is the network. Okay. So that was what we discussed the other week. Okay. Today we shall be looking at detection of autocorrelation. All right. Remember that I said when you have autocorrelation is more or less like a patient that is sick. Okay, a patient that is sick goes to the hospital. The first thing the patient will do is to conduct a test. All right, and when you conduct that test, you will be able to discover, okay, where you'll be able to discover where you are actually not feeling too well, or oh, okay, let me enable the recording. Okay, just 1 minute, please. Oh, it's recording already. All right, Jonathan, sorry, it's recording already. Okay, so when we have the case of autocorrelation, all right, it is just like for a patient that is sick, and when the patient is sick, the patient does not have option but to actually go to where? Hospital. The same way it is for a time series analysis. For a time series analysis, the same analysis is what we have to do. Whenever we, kind of sense that there is autocorrelation, what we have to do is to conduct tests. Just like a patient that is sick goes to the hospital, you must conduct what? A test. Having said that, okay, um, having said that, the next thing we'll now look at is how do we conduct the test, all right? In conducting the test, there are two ways that we can actually use to conduct the test. One, we have the informal way, all right? And the second one is the formal way. Just like a patient that is sick, informally, oh, the patient is having high fever, the patient is having body pains. Oh, it might be, or it might likely be malaria. In that same vein, that is also how you also conduct a test for autocorrelation. All right. The first one is informal way. Remember that if there is autocorrelation, the implication of this is that the error term at one period, all right, has a relationship with the error term at another period. So very simple. What do we do? We can, in the same vein, conduct a test for what? Autocorrelation. How do we do that? You just estimate your OLS regression. When you estimate your OLS regression, you retrieve the error term. Then when you retrieve the error term, remember that when there is autocorrelation, that means there is a relationship between the error term at one period and at the other period. Plot a graph of those two error terms. And when you plot a graph of those two error terms, once there is a similar pattern in that graph, then we can say that there is what? Autocorrelation. Okay? Let me explain further by looking at what we have to do. For example, we know, okay, that when there is autocorrelation, we say that the error term, okay, we say that the error term at period t and then the error term at period t minus 1 exhibits a relationship, okay? The error term at period t and the error term at period t minus 1 exhibits a relationship. What does that mean? It means that if you estimate the equation, say error term, if you estimate the equation, say error term ut is equals to rho. This rho is like a coefficient. The way you have your x, your beta 0, your beta 1, that's just like a coefficient. It means when you estimate the relationship between the error term t and rho and error term t minus 1, you are going to have a statistically significant coefficient of the rho. If this rho, all right, is significant, we say there's autocorrelation. So what do we do? The first thing we do is for us to estimate our model. When we estimate our model, we generate the error term. When we generate the error term, you then compare the relationship between the error term at one period and at the error term at another period. All right. So let's take an example now. All right. And let's look at this. I have a data, okay, that I downloaded from the CBN Statistical Bulletin. If you look at that data, you would see that I have a data, all right, that has a GDP, okay, of Nigerian economy from period 1981 down to 2019, all right? And then I also have government expenditure for Nigeria from 1981 down to 2019. In the same vein, I have investment, trade balance, inflation, and exchange rate, okay? So that means I can decide to estimate a model whereby my GDP is my dependent variable. And then all of this, the government expenditure, the investment, the trade balance, inflation, and exchange rate, they are my independent variable, all right? And so if I want to write that equation, I would definitely say that my model, all right, is my model is what? GDP, okay, is equals to beta 0, all right, plus beta 1, government expenditure, okay, plus beta 2, investment, okay, plus beta 3, trade balance, okay, plus beta 4, inflation, all right, and then plus beta 5 in exchange rate, sorry, plus beta 5 exchange rate, okay? Then plus my error term, all right? This model can be likened to our normal macroeconomic framework, just a breach of our macroeconomic framework. All right. The abridged of our macroeconomic framework is what? GDP is a function of government expenditure. All right. Is a function of what? Investment, trade balance. Then we can bring in inflation and exchange rate. Of course, you know that our normal macroeconomic framework is y equals to c plus I plus g plus x minus m. The x minus m there is trade balance, which is export minus import. Okay. The government there expenditure is the g. Your investment is I. So I didn't capture consumption under this model. So let's assume this is a typical model, all right? And I've been able to generate the data from 1981 down to 2019, sorry, from 1981 down to 2000 and what? 19. And so the next thing I want to do is I want to graphically, using an informal way, to actually dictate if there is autocorrelation. So what do I do? The next thing I will need to do is let me first of all save this. So the next thing I will need to do is I will need to, let me just exit, okay? I will need to go back to my Excel sheet, the data I've already collected, okay? What do? I will copy the data, all right, and I will estimate. So that means I believe, or I should believe, that you know how to estimate a model. You have been taught your OLS regression model. You have been taught. So I believe you know how to estimate the model, okay? So I would copy my model, all right? And when I copy my model, I will simply go to where? My eViews, all right? I will go to my eViews. Then I will create a new work file. I'm not going to teach you this because there is no time. We don't have that time to be teaching you all of this, but I assume you know how to do that. I create my work file, okay? My work file is for between the periods is for between the periods 1981 to 2019. Okay, I've created my work file. I import my data. All right, so I have my data. What's the next thing I will do? The next thing I will do is to estimate my model. Remember my equation that I've said, okay? I would estimate the equation. And my equation is that what? GDP is a function of exchange rate, government expenditure, inflation, investment, and trade balance. I can decide to log my variables because when you see those particular data, they are large. So when the data is large, for me to smoothen it, I need to log it. You must have been taught, okay? Exchange rate is in 300 and something naira, 200 and something naira, okay? Government expenditure is in billion, GDP is in billion, investment is in billion, trade balance is in billion. So I need to log them, all right? In my eViews, I can just easily type my log, open a bracket, and then I start with my what? Dependent variable. I give a space. My C is my intercept. I believe you should have been exposed yourself to this. And then I input my government expenditure. These are my other explanatory variables: government expenditure, my investment, okay? And then I have my exchange rate, okay? And then I have what? I have inflation. Then I won't log trade balance because if I log trade balance, we have negative numbers. So when I log it, it's going to be negative, and I can't log a negative number. So I estimate my model, and that's my result. All right. Immediately I've estimated my model, this residual is my error term. It's automatically generated in eViews. Each time you estimate your model, the error term is automatically generated, and that is my what? Error term. So I double click on it. This gives me my what? My error term, okay? So I can just copy this error term from my eViews. Remember, the eViews is used so that I can actually do what? Estimate my model. I will go there to retrieve my error term. Instead of me start start typing beta 0 equals to y bar minus beta 1 x bar minus this. Instead of me to be writing beta 2 equals to n summation x summation, I can just use my e-views and estimate, and I generate my what? My error term. I copy it, okay? So if I generate my error term and I copy it, I take it to my what? Excel environment, all right? When I take it to my Excel environment, all right, I can easily paste it up so that will be my what? Error term. Then I paste it here, okay? Let me bring in my years. Remember, it's from 1981, all right? It's from 1981. Let me just convert this to numbers so that it will just be in form of years, okay? It's from 1981, and then we have 1982, okay? And then I can easily drag it down, all right? I can easily drag it down, okay? And I convert them to general. Let me just convert them to general. So this is what? The error term, okay? Let me bring it up. This is the error term. So this is just like mu t. Remember, your error term, okay, is always equals to what? Your y estimate, yt minus y at. That is it. The next thing is I need to look for error term at previous period, okay? I will lag it, abi? Because if there's a relationship between the current error term and the previous error term, I can conclude that there is what? Autocorrelation. So if I'm to lag it, this is error term t. And if this is error term t minus 1, when I'm lagging it, that means for this present year, there is no previous. But for this present year, there is a previous error term. That means this particular value becomes this error term. This particular value becomes this error term. This particular value becomes this error term. So I can just easily copy these particular values, okay? When I copy them, I can easily come and paste them here. Just take it one step further down and paste. So that means this is the current error term in the cell J, and this is the previous error term. Look at it. The error term in 1982 for the lag is the error term in 1981. The error term in 1980, 81, 82. Oh, that's an error. Let me just correct these. Let me correct this numbering. Sorry, please. Yeah, okay. So the error term in 1981 becomes the error term in 1982 when it is lagged. Have you seen the way you can lag your variables? Okay. So what do you do? Very simple. Plot a graph between these two particular series. Remember that for this, there is no 2020, so you wouldn't have any error term for that period. That means whenever you lag your variables, you will always have degrees of freedom that you are losing. Then what do? You plot the graph, okay? You can just plot the graph. Now, look at this graph. You would see that there is a similar pattern in this relationship. What next do? You can plot a trend line to see. Look at it. You will see that the error term at the previous period is somehow related to the error term at the current period. The error term in 2019 is related to the error term in 2018. The error term in 2018 is related to the error term in 2019. The error term in 2019, the lag period continues. And look at it, there's an upward trend. That means there is a relationship between the error term now and the previous error term. Looking at this sketch, you can easily conclude that there is a positive autocorrelation. All right. So what that means is that using the informal method, what happens whenever you have a relationship between your error term exhibiting a similar pattern, somehow like this. You can also have a relationship between your error term. Remember, this will be your error term T. This will be your error term T, okay? Error term mu T minus 1. And it follows that same pattern. And then you have another relationship like this. You can also have another relationship that is in this form. And then you can have a relationship that there is no pattern, no unique pattern, okay? Under this first scenario, I can call this A, I can call this graph B, I can call this graph C, and I can call this graph D. For this graph A, you will see that there is an upward trend between the current error term and then the previous error term. So what can we say from here? We can easily conclude that there is positive what? Autocorrelation for this first one. All right. And then for this second one, we look at this particular error term and we'll see that there is a negative relationship between this error term and that previous error term. This particular relationship is inverse. So we can conclude that there's what? A negative autocorrelation between those error terms. Then look at this graph C. For graph C, it is somehow cyclical, all right? And that also shows a similar pattern, and we can conclude that there's what? Autocorrelation. Then for this graph D, there is no relationship because there is no unique pattern that graph D is following. That means when you estimate your model and you generate your error term, and you just plot a graph between the current error term and the previous error term, what happens? You can conclude if there is autocorrelation by looking at the pattern that it follows. That is the first way of detecting what? Autocorrelation. And under this format, we say it is the informal way of detecting what? Autocorrelation. All right, so let's look at the second way. All right, the second way is now the formal way. All right, and that is when you actually conduct a test. Remember, the informal way is, oh, your body is hot, take malaria drugs, take paracetamol, maybe stress, sleep. That is informal. Remember that in the medical profession and in a civilized clime, you are always advised to consult your doctor. The doctor will now recommend tests for you. So the informal way is just to look at it, a slight headache, probably is tiredness, take some pain relief and rest. The second way is the formal way, and that's where you actually conduct tests. So different scholars have identified different strategies of conducting the test. There are many of them, but we are only going to limit ourselves to three. The first one is the Runge test. All right. The second one is the Durbin-Watson test. And the third one is the Bush-Godfrey test. These are the three methods that we are going to what? We are going to use. There are still other many methods, okay? But however, we are only trying to limit ourselves to this particular three. All right, so let's look at the Runge test. From my slide, you can see the Runge test developed by Jerry, okay? This Runge test tries to just do one thing. The Runge test tries to look at the pattern of positive values and negative values in our error term. That is the first thing it does. Let me go back to our Excel file. We are going to be working pretty much with our Excel file, okay? Now, remember, this is my Excel file. Let me copy this. Remember that I've already used this to plot a graph, so I don't want to kind of interfere in the graph. That is why I want to paste it somewhere else, okay? So that I can easily work with it, okay? Remember, this is my error term. Remember that particular theory that will say that the expectation of your error term is 0. If you remember the OLS assumption, if that is the case, that means if you sum this error term, all right, what happens from N2 down to where N40? Of course, you will see that it is what? 0. N2 down to N40. When you sum it, approximate it, okay? Look at it. You see that the summation is 0. So that means this assumption 1, assumption 2, that the expectation of your error term is 0 actually holds for this particular model. All right, okay. Now, Ron's test simply tries to look at the pattern of your error term. How many of them are positive? How many of them are negative? How do they change frequently? For example, in 1981, you will see that the error term is what? Is positive, okay? Cecilia, I'm coming. I will attend to you, please. Then in 1982, it was negative. 83 negative, 84 negative. 1985 down to 1993, it was positive. 1994 down to 2007, they were all negative, all right? And then 2008 down to 2016 was positive, and then 2017 to 2019 was negative. Now, how frequent does this particular error term changes sign? That is the Ron's test. The number of times it changes sign tells you the number of what? Of runs that we have. Okay, let me stop because I've got someone raising up a hand. um Cecilia, okay, please let me unmute you. What's your question, please? Olamide Adedeji, Cecilia, you raised your hand. Do you have a
Good
question?
afternoon, sir. I can't hear you, sir.
Oh, but can't you hear me now? I'm sorry, please. Maybe you try to look into your network, please. Try and look into your network, okay? All right. Please, class governor Kayode, I don't know. Are there people that are outside that want to come in? I don't think there are any of them. Okay. So let's go back to our explanation, all right? Let's go back to the Excel. You will see from here, this one was positive, okay? This was positive, all right? From here down to here is negative. So we have the second time it changed to negative, okay? From here down to here is positive, okay? It became positive. From here down to here is negative, okay? From here down to here is positive, okay? From here down to here is what? Negative, okay? That means we have how many runs? 1, 2, 3, 4, 5, 6. There are 6 runs in this particular example, okay? Meaning the error term changed sign in 6 ways, okay? Then look at my notes that I put on my slide. Look at this note, okay? I said something in this slide, all right? I said, if there are too many runs, that means if the error term changes sign frequently, it would mean that in our example, the residuals change sign frequently, thus indicating negative serial correlation. Similarly, if there are too few runs, that means it didn't change sign frequently, we can suggest there is what? Positive what? Autocorrelation. So that means if it changes sign too many times, there is negative. If it changes sign frequently, there is what? Less frequently, we say there is what? Positive. So in this our example, we have how many runs? We have 6 runs. R equals to 6. That's our example. We have 6 runs. Our runs in this example is 6. We can't just conclude from this that, oh, there's positive autocorrelation or negative. We can't. There's a need for us to test that runs. It's important that we test what? We test the runs. And we need to test that runs to see how statistically significant is the runs. I remember that I've taught you extensively in your hypothesis testing in your year 2, and I said you are going to be using it so many times in your econometrics for year 3. So there's a need for me to test for the statistical significance of my runs. Okay, how do I do that? You remember that in our hypothesis testing, okay, under our hypothesis testing, we simply say that for us to test Moyo, Moshood, please, I will come back to you. For us to test for our hypothesis testing, we simply say, all right, that our statistics, maybe T statistics, if you remember, is equals to the mean, all right, of your. I was off in the other platform. I'm back here now. Okay, so sorry.